All right, guys. So previous वाली class के अंदर, as I said, we concluded the working of magnetism. So now the next working is concept of electromagnetic induction. तो इसमें क्या क्या चीजें डिस्कस करनी है ना, थोड़ा सा क्विकली इसको गो थ्रू कर लेते हैं. So the first working, and this working is kind of based on the idea जो तुम लोगों ने O levels में किया हुआ था. At least नाम तो याद ही होता था. So that was referred to as Faraday's law of electromagnetic induction. मैं जरा रीड थ्रू कर लेता हूँ और फिर साथ साथ एक्सप्लेन कर दूँ. Regarding Faraday's law, तुम लोग O levels में ये working करते थे. You are given a brief idea. Let's suppose if you have a magnet, and imagine if a magnet is positioned right beside the solenoid. So तुम लोग O levels के अंदर ये चीजें पढ़ के आते थे कि when the magnet is going to be pushed inside the solenoid, you would expect that the voltmeter is going to give a deflection in one particular direction. Then you were also taught that when the same magnet is going to be pulled out of the solenoid, once again, a deflection is going to be observed on the screen of the voltmeter, but this time in the exact opposite direction. So, iski basis par, in O levels, the Faraday's law was kind of written along these lines, that the change in cutting effect, these were the precise wordings जो आप लोग use करते थे. The change in the cutting effect between the field lines and the coils of the solenoid induces EMF in the circuit. और reasoning हम लोग ये देते थे, if I were to construct the field lines, let's say if I were to use a green colored marker or a blue colored marker rather, थोड़ा सा prominent हो जाएगा, to show the field lines. So the magnetic field lines coming out of the North Pole can be represented as shown over here. So both when the magnet as it is pushed in, or for that matter, when the magnet is pulled out, so whether it's pushed in or it's pulled out, there is certainly going to be a change in cutting effect between the magnetic field lines and the coils of the solenoid. And this change in cutting effect, based on the theory of O levels, was responsible for inducing EMF in the circuit. The Faraday's law, हम लोग इस तरह से O levels में suggest करते थे. अब extending this idea further, so A2s के अंदर थोड़ा सा इस wording को हम लोग kind of adapt कर लेते हैं. So A levels के अंदर, the same Faraday's law is now represented in a slightly modified version. So wordings आपकी ये बन जाती है कि the rate of change of magnetic flux induces EMF in the circuit. So the so-called term magnetic flux, इसको आप O levels में बोलते थे change in cutting effect between the field lines and the coils of the solenoid. So that term kind of reduces down to just a simple term, magnetic flux. And the Faraday's law, if now executed, it will be represented by the term rate of change of magnetic flux is responsible for inducing EMF in the circuit. So magnetic flux क्या होता है ना, जरा उसको define पहले कर लेते हैं. So here there are three terms, and I guess it is very relevant at your stage कि आपको इन तीनों terms की एक clear distinction होनी चाहिए. So मैं screen पे पहले ये तीन terms identify कर दूं. So the first term is magnetic flux density. The terms are kind of so similar कि आप लोग इन सारे terms को interchangeably use कर रहे होते हो, failing to realize कि सब में थोड़ा थोड़ा difference है. So the first term, magnetic flux density. Then the second term, जो predominantly हम इस topic में use करेंगे, magnetic flux. Kind of similar with a slight bit of a difference. And then the third one, magnetic flux linkage. तीनों का difference क्या है? So starting with the first terminology, बिल्कुल simplest form में, starting with the first term, magnetic flux density is just an alternate name used for magnetic field strength. The strength of the magnetic field can simply be referred to as magnetic flux density. It is denoted by the symbol of B, and it is measured in units of Tesla. So magnetic flux density is just an alternate term used in place of magnetic field strength, denoted by the symbol of B, measured in units of Tesla. Then moving on to the second term, just the term magnetic flux. So magnetic flux is denoted by the symbol of phi, and it is defined as the product of magnetic flux density B and the area A of the coil through which the field is passing, provided that the area is perpendicular to the field lines. So magnetic flux denoted by the symbol of phi, it is defined as the product of magnetic flux density B and the area A of the coil through which the field is passing, provided that the area is perpendicular to the field lines. तो अगर मुझे इसको diagrammatically show करना हो, so in the diagram below, I've shown the strength of the magnetic field to be B Tesla, and the magnetic field lines are shown with the black colored marker. Okay, so diagram pe, the horizontal lines are the magnetic field lines, the strength of which is B Tesla. In this magnetic field, I have positioned an area. The area is the green colored portion. That area is denoted by the symbol of A. So based on the wordings, magnetic flux phi is defined as the product of the field strength B and the area A through which the field lines are passing, provided that the area is perpendicular to the field. So in the first layout, the magnetic flux phi, based on the definition, it can be written as B times A. The second scenario के अंदर, since the area is no longer perpendicular, rather the area is now parallel to the field lines. So now there is no cutting effect established between the area and the field lines. Consequently, magnetic flux in the second scenario is zero. और third वाले case के अंदर, where the area, as you can notice, is making an angle of theta with the field lines. तो फिर यहाँ पर आपको area को resolve करना पड़ेगा. तो component में draw कर देता हूँ diagram के ऊपर, वो follow कर लो. So the component in the diagram, I've represented that by the term A sine theta. And consequently, for the third case, the magnetic flux phi will be written as B times A sine theta. Technically तो तीनों formulas learn कर लीजिएगा. But out of the three, I think जो first वाला result है ना, जिसको मैं yellow वाले marker से highlight कर रहा हूँ, essentially उसकी relevance थोड़ी ज़्यादा है. ठीक है, so up till now we have seen that the strength of the magnetic field is alternately called magnetic flux density. Then magnetic flux is denoted by the symbol of phi, and it is defined as the product of the flux density B and the area A through which the field lines are passing, provided that the area is perpendicular to the field. So the result turns out to be phi is equal to B times A. Now moving on to the third statement, magnetic flux linkage. तो इसका क्या मतलब बनता है? So statements पहले read कर लो. So if your coil consists of a large number of turns, example, if your coil consists of n number of turns, then the cutting effect established is given a special name known as magnetic flux linkage. So if your area, basically simple terms में, if your area consists of a large number of turns, like in this case, अभी show कर देता हूँ कि if the area comprises of n number of turns, then the cutting effect established is given a special name known as magnetic flux linkage. This is also denoted by the same symbol of phi, and the formula gets slightly tuned up. So instead of BA, sorry guys, the formula now becomes n times b times a, where n represents the number of turns. अगर आपको diagrammatically show करना हो ना, तो मैंने उसको नीचे अलग से बनाया है. So if you want, you can actually make a comparison between the top diagrams versus the one that is appearing on your screen right about now. Almost same diagrams hai, with the exception of the fact that the first three diagrams ke andar, the coil comprises of a single turn, whereas in the final diagram or the final layout, I'm using large number of turns. तो मैंने coils के बहुत सारे multiple turns बनाए हुए हैं. So basically, अगर आपको distinction करनी हो, तो I think इस तरह से learn कर लेना कि magnetic flux density is just another name for magnetic field strength. Which is second statement. The cutting effect established for a single turn of wire is known as magnetic flux. And the cutting effect established for a large number of turns of wire is called magnetic flux linkage. One is given by the formula BA, while the other one is given by the formula NBA. Okay, so magnetic flux cutting effect established using a single turn of wire. Magnetic flux linkage, on the other hand, cutting effect established for a large number of turns. So one given by the formula B times A, the other one given by the term N times B times A. Now, as far as units are concerned, I'm sure आप agree करोगे ये phi के units अगर आप formula को देखोगे ना, apparently N doesn't have any units. So number of turns के तो कोई units नहीं होते, it's a dimensionless quantity. B के लिए Tesla, area के लिए meter square. So on the basis of this result, आपका final answer आ जाएगा Tm square. So Tesla meter square, Tm square. Otherwise, the more commonly used units for phi is Weber, WEBER, denoted by the symbol of WB. So you can go with either of them, Tm square, Tesla meter square, otherwise Weber, denoted by the symbol of WB. Now, extending this idea further, अब जो Faraday's law मैंने ऊपर लिखा हुआ था ना, उसकी जरा एक mathematical formulation कर लेते हैं. So the formula was rate of change of magnetic flux induces EMF. So अगर मैं इसको mathematical terms में लिखूं, I'm sure you would agree. There are multiple ways of writing down this result. So induced EMF is equal to rate of change of magnetic flux. So basically a change in magnetic flux upon time. फिर जो भी आपको सूट करे. This can further be written as, हो सके तो सारे याद रख लेना, delta phi upon t. So change in flux, delta phi upon t. If you were to further simplify, so delta phi can be written as a final value minus the initial value upon time. अच्छा, काफी students इसको flip करके ऐसे भी लिख देते हैं. And technically there is no harm in it. So it doesn't have to be final minus initial. Even if you want to write it down as initial minus final, you'll end up getting the same change. So कोई issue नहीं है. So final minus initial सही लगे तो go with that. Otherwise initial minus final जैसे भी सही लगता है. और अगर आप इसको purely mathematical sense में लिखोगे ना, तो इसको इस तरह से भी लिख सकते हो. ये लास्ट वाला फॉर्म आई थिंक जो मैथ्स करते हैं आई थिंक उनके लिए जरा ज्यादा सूटेबल है. जो रेड से मैंने लिखा है ना, प्योरली अगर आप मैथमेटिकल टर्म्स में सोचते हो तो रेट ऑफ चेंज मैथ्स में पढ़ते थे डिफरेंशिएशन के अंदर. So rate of change of magnetic flux can be represented as d phi upon dt. Okay, Riha, capital E is for EMF induced. तो EMF के लिए वी आर यूजिंग द एग्जैक्ट सेम सिंबल जो O levels में यूज करते थे, इफ यू रिकॉल. सो EMF was denoted by the symbol of capital E. Hence मैंने उसी टर्म्स में लिखा हुआ है. ठीक है. ऑल राइट. हो सके तो सारे रिजल्ट्स याद रख लेना, और डेल्टा फाइव अपॉन टी कम से कम एक याद रख लो. फिर ये याद रख लेना कि इट कैन बी फाइनल माइनस इनिशियल, और इट कैन इवन बी इनिशियल माइनस फाइनल, जो भी आपको सूट करे. नाउ हाउ डू वी अप्लाई दिस फॉर्मूला प्रैक्टिकल सिनेरियो के अंदर? सॉरी गाइस. तो यार फॉर्मूले को अप्लाई कैसे करेंगे ना, उसके लिए व्हाट आई हैव डन इज, मैंने एक डायग्रामेटिक रिप्रेजेंटेशन करी है. तो पहले जरा डायग्राम अंडरस्टैंड कर लो. तो स्क्रीन के ऊपर you are able to see a coil consisting of large number of turns, the red one. It is connected to a voltmeter. अच्छा, एग्जामिनेशन पर्पसेस के लिए दिस काइंड ऑफ अ कॉइल, मैं इसको अगर आप चाहें तो सेपरेटली भी बना देता हूँ. सो एग्जाम्स के अंदर दे कैन आइदर यूज द टर्म अ कॉइल कंप्राइजेस ऑफ अ लार्ज नंबर ऑफ टर्न्स connected to a voltmeter, like the way I just stated. तो अगर आपको सूट करे तो remember it this way: coil comprising of a large number of turns connected to a voltmeter. It's perfectly all right. बट यूजली एग्जाम्स के अंदर व्हाट दे डू इज कि वो इतनी लंबी चौड़ी वर्डिंग्स लिखते नहीं है. और सीआईस के अंदर अ कॉइल कंप्राइजिंग ऑफ अ लार्ज नंबर ऑफ टर्न्स कनेक्टेड टू अ वोल्टमीटर, द वन व्हिच आई हैव कंस्ट्रक्टेड सेपरेटली, in your CIEs they just refer to such a coil by the term surge coil. Examination point of view से generally they don't end up writing down the entire statement. That कभी कभी लिख भी देते हैं कि a coil comprising of a large number of turns connected to a voltmeter, something along those lines. लिख भी देते हैं, लेकिन usually shorter version के अंदर they just refer to that by the term surge coil. सही. So in the diagram, और मेरे लिए भी I think कहना convenient हो जाएगा. So in the diagram there is a surge coil given to you. मैंने उसकी initial position label करी है, मैंने उसकी final position भी label करी है. So what we are doing is कि in order to bring about a change in cutting effect, or you can say in order to bring about a change in magnetic flux, मैं coil को move करूंगा. So I'll start moving my surge coil from its initial position to a final position, with the intention of bringing about a change in cutting effect or a change in magnetic flux. Now, the details given to us are as follows. The area of the surge coil is provided. The strength of the magnetic field at the initial position is given. Final position pe, the strength has increased, as you can see from the diagram. Number of turns be given hai. And the time taken for me to move this coil from the initial to the final position is also provided. So in this case, you are expected कि यार आपको calculate करना है how much is going to be the induced EMF. You know वो जो top पे formulas लिखे थे ना, and I guess I'll probably go with this result. फिर simplify कर लूंगा. So I'll go with delta phi upon t. Apply कैसे करेंगे ना वो देख लेते हैं. So assuming कि formula आपको याद रह ही गया होगा, तो working का result इस तरह से बन जाएगा. Numbers बाद में लगा देता हूँ. रोहेल यार जरा कैलकुलेटर पकड़ना, या अली तुम देख लो बेटा, अदरवाइज इफ आयशा इज देयर वो मेहनत कर लेगी. सो पहले जरा सिंबल्स देख लो. सो फाइनल के लिए आई एम यूजिंग द फॉर्मूला NBA. लाइकवाइज इनिशियल के लिए मैं वैल्यूज लगा देता हूँ. आई कैन टेक आउट नंबर ऑफ टर्न्स कॉमन. द एरिया ऑफ क्रॉस सेक्शन, दिस नीड्स टू बी कन्वर्टेड. थोड़ा सा जूम आउट कर रहा हूँ. So the final position was 180. The initial position was 70. The values were in millitesla. Time was 0.1. So simplification देख लेना. I've taken out number of turns common. I've taken out the area common as well. मैंने SI units में appropriately सबको convert कर दिया है. So the induced EMF, or you can say the reading on the voltmeter, amounts to, हाँ यार, कुछ आ जाए तो बताते जाइएगा, फिर मैं नेक्स्ट डायग्राम पे मूव करता हूँ. 0.44. Thank you, Amar. ठीक है, what this answer is telling us is कि this answer is कि when you move this search coil from its initial position to a final position, because of the change in cutting effect or because of a change in magnetic flux, the EMF induced or the voltage produced amounts to so and so volts. So 0.44 volts is the amount of induced EMF because of a change in magnetic flux as the coil moves from its initial position to its final position. जी, अब जो रायान ने लिखा है ना, एक सेकेंड ना हुसैन, पहले मैं रायान को आंसर दे दूं. हुसैन तुम भी क्वेश्चन को एवरीवन पे सेट करके दे दो. सो जो रायन का क्वेश्चन है ना कि यार इफ आई वर टू मूव इट द अदर वे अराउंड, so instead of moving it from left to right, if I were to move it, let's say from right to left, जो रायन कह रहा है, I'll end up getting the exact same answer but with a negative sign. That negative sign would simply implicate that the voltmeter, if previously it was giving a deflection in one direction, that the negative sign kind of implies that the voltmeter is now going to deflect in the exact opposite direction. And technically speaking, that doesn't really concern us, which is why I said कि आप फाइनल माइनस इनिशियल लिखो या इनिशियल माइनस फाइनल लिखो, मैग्नीट्यूड वाइज तो रिजल्ट आपका सेम आ जाएगा. ठीक है, सो नेगेटिव आंसर इन सच केसेस just implies that the voltmeter is going to deflect in the exact opposite direction. जी, जिसको रोहेल ने नेगेटिव लिखा है. So हुसैन ने कहा था when you see large number of turns, what can be a minimum? A few hundred. So at least 100 or more. All right यार, अब आगे प्रोसीड करता हूँ. अच्छा अगर मैं डायग्राम को थोड़ा सा चेंज करके इमेजिन करें, अगर आपको टॉप का डायग्राम भी देखना है ना, तो आई जस्ट जूम आउट अ बिट ताकि आपको दोनों नजर आ जाए. ऑल्दो स्क्रीन साइज थोड़ी छोटी हो जाएगी, लेकिन आई डोंट थिंक इट मैटर्स फॉर द टाइम बीइंग. जस्ट हैव अ लुक एट बोथ द डायग्राम्स. और आई एम श्योर आप अग्री करोगे कि इन द फर्स्ट डायग्राम, द डायग्राम ऑन द टॉप ऑफ योर स्क्रीन, the field is of a non-uniform nature, whereas if you pay attention towards the diagram at the bottom of the screen, the field is of a uniform nature. अगर मैं आपको सेकंड वाले डायग्राम में सेम क्वेश्चन पूछूं कि the search coil is moved from its initial position I to its final position F. And in the second diagram, the one at the bottom of your screen, if I were to ask you how much EMF is going to be induced, so जो मुस्तफा ने आंसर दिया है 0 volts, that kind of makes the most sense. And the reason as to why we should be agreeing with Mustafa that the induced EMF in this case is going to be 0 volts is because look carefully. You can't expect any change in cutting effect because जितना कटिंग इफेक्ट इनिशियल पोजीशन पे स्टैब्लिश हो रहा था ना, सेम उतना ही कटिंग इफेक्ट फाइनल पोजीशन पे भी स्टैब्लिश हो रहा है, बिकॉज द सेम नंबर ऑफ फील्ड लाइंस आर कटिंग द सर्च कॉइल both when it is in its initial position and when it is at its final position. So I think you would all appreciate कि अगर फील्ड यूनिफॉर्म हो तो यूनिफॉर्म फोल्ड फील्ड में ये प्रॉब्लम अराइज करता है कि इट इज काइंड ऑफ डिफिकल्ट टू जनरेट अ कटिंग इफेक्ट by simply moving the coil linearly. तो लीनियर मूवमेंट का सेकंड डायग्राम में कोई खास फायदा नहीं हो रहा, hardly any advantage, because we are not able to establish any change in magnetic flux. So rightly so, induced EMF in this case is going to be 0. And the reason should be along these lines. No change in magnetic flux. However, if for the same diagram, अब मैं थोड़ा सा zoom in कर रहा हूँ और मैं top पे move कर रहा हूँ. So if for the same diagram, if I were to ask you, कि what if instead of moving the coil linearly, what if I were to rotate the coil? Then I'm sure you'd appreciate कि rotation करने का फायदा definitely होगा. Imagine if I were to say I'm rotating the coil, let's say by an angle of 90 degrees. So can you recognize अगर आप coil को 90 डिग्री से rotate करोगे ना, तो मैंने इसका diagram show कर दिया है. So initially it is positioned in a horizontal plane, or finally after a rotation of 90, the coil aligns itself in a vertical plane. So from its horizontal position, a rotation of 90 makes it reach a vertical position. इस case में we can definitely expect change in cutting effect होगा. And the reason for that would be, for the initial position, you would all agree that the value should be 0. Why 0? In case if you're wondering. So the answer should be because the plane of the coil is parallel to the field lines. So the plane of the coil is not cutting the field lines. Okay, so initial position is 0. Final position pe, now the plane has become perpendicular to the field lines. So NBA. So now if you're asked how much EMF is going to be induced, so surely your answer is not going to be 0. So the induced EMF in this case. अच्छा कुछ लोग लिखते हैं the change will be NBA. So NDA upon T, or equally correct if you want to write it down. The second option is equally correct, minus NBA upon T. The reason why they accept both the answers is because it's entirely up to you whether you opt for final minus initial or you go for initial minus final, जो भी आपको suit करे. So in the diagram which I'm highlighting with the pink marker, where the field was uniform, it's pretty much apparent कि linear movement का कोई फायदा नहीं होगा in a uniform field. Because there is no apparent change in magnetic flux. However, rotation does help. So rotating the coil, let's say through an angle of 90, the change established हो रहा है because at 0 degrees, the plane of the coil was parallel to the field lines. Here after 90 degrees की rotation, the plane becomes perpendicular. So initial value was 0, final is NBA. So the change definitely occurs and the result has been indicated. अच्छा रोहिल ने wording सही लिखी है, from minimum it goes to maximum. So that's fair enough. अच्छा I'm sure आप इस बात से भी agree करोगे कि अगर मैं 180 मैं 90 के बजाय if I would have asked you ना यार what if I were to rotate the coil through 180 degrees, अब आपका change kind of double हो जाना चाहिए. So in case if you're wondering now कि मैंने double क्यों बोला, तो I think इसका best understanding ऐसे हो सकती है कि आप 180 की rotation को 2 fragments में break कर दो, 0 to 90 and then 90 to 180. So rotation through 180, think of this as twice the previous answer. मैं लिख भी देता हूँ. So basically 0 to 90 and then 90 to 180. So यह result आपके पास workout करके आ जाएगा और twice the previous answer का मतलब है ये रिजल्ट आ जाएगा। अच्छा, मैं हमेशा स्टूडेंट्स को ये चीज रिकग्नाइज कराता हूँ कि ऑल्दो ये फॉर्मूला आपने ओ लेवल्स में नहीं किया, लेकिन आप सब ने ये कॉन्सेप्ट ओ लेवल्स में पढ़ा था, दिस आइडिया ऑफ रोटेशन। एंड सभी भूल चुके होते हैं, और काफी लोग तो कहते नहीं पढ़ा ही नहीं था, बट दे कंप्लीटली फेल टू रियलाइज कि डेफिनेटली ये पूरा कॉन्सेप्ट आपने पढ़ा था कि रोटेशन से ईएमएफ इंड्यूस होता है। और अगर भूल गए हैं ना, दिस वर्किंग वाज डन इन ओ लेवल्स, नॉट ए, ऐसा माइंड यू, अंडर दिस हेडिंग, प्रिंसिपल्स बिहाइंड द वर्किंग ऑफ एन एसी जनरेटर। जरा गौर से सोचिए, आप एसी जनरेटर के अंदर क्या चीज ओ लेवल्स में पढ़ते थे, और आपने लिटरली यही आइडिया पढ़ा था जो मैंने अभी एक्सप्लोर किया है, जस्ट विद अ स्लाइटली डिफरेंट पर्सपेक्टिव। ये चीज आपने की थी ओ लेवल्स में। अच्छा, I'm not really keen in drawing the diagram of an AC generator, but just to give you a basic layout, you were given this idea. If there are two magnets, one positioned on one side, the other one positioned on the other side, then you were also given this idea that between the two magnets, हम लोग एक coil को लाके रखते थे, और अगर आपको याद हो तो the coil was made to be rotated between the magnetic poles. And technically, if you think along the lines, जो coil आपकी coil rotate करेगी between the magnets, तो क्या होता था? So you were taught this in O levels, that as the coil is going to rotate between the magnetic field, there is going to be a continuous change in cutting effect, and that will induce EMF. So that was the principle behind the working of an AC generator. So this idea of rotation, it might sound different or unique to you, but O levels ka idea, the basic working principle of an AC generator, was derived from this concept. Okay, so in a uniform magnetic field, the idea of rotating the coil with the intention of generating EMF does make sense. सही। और अच्छा, उमर ने एसी से ही लिखा और आगे मोटर लिख दिया। सो उमर, वो दैट वाज एक्चुअली डीसी मोटर एंड इट वाज एसी जनरेटर। तो तुमने आधा टर्म एक जगह से निकाला और बाकी आधा दूसरी जगह से निकाल लिया। ठीक है, बट यस, योर आइडिया वाज काइंड ऑफ करेक्ट। सो एसी जनरेटर, है ना, द आइडिया बिहाइंड जनरेटिंग इलेक्ट्रिसिटी by using this principle of turning effect. Anyways, नेक्स्ट वाली स्लाइड पे मूव कर रहा हूँ, सो थियोरी को आगे कंटिन्यू कर लूँ। मैं बाद में लेबलिंग कर दूंगा स्लाइड्स की। सो नेक्स्ट चीज ये डिस्कस करनी है, ओके। सो वंस अगेन, डायग्राम के अंदर द सर्च कॉइल इज गिवन टू यू। आई हैव शोन द इनिशियल पोजीशन ऑफ द सर्च कॉइल। मैं इनिशियल वाली पोजीशन को पिंक कलर से हाईलाइट कर रहा हूँ, ठीक है। देन द फाइनल पोजीशन ऑफ द सर्च कॉइल इज आल्सो शोन, ठीक है। सो फ्रॉम द इनिशियल पोजीशन, आई एम मूविंग द सर्च कॉइल to its final position. So arrow pointing from left to right, basically. And as the coil moves, there is a region of uniform magnetic field, which I'm highlighting right now. So the coil is being moved from its initial to a final position from left to right. And as the coil begins to move, it will enter and it will exit a uniform magnetic field. Entry point is labeled as A, if that makes sense to you, or exit wala point is labeled as B on the other side. Now the question is asking you, यार आपको ये सजेस्ट करना है कि as the coil moves from left to right, L to R, sketch a graph to show how induced EMF varies with the distance moved. So on the vertical axis, induced EMF horizontal axis, distance moved. ठीक है, and for your convenience, I've labeled 2 points A and B. So point A के ऊपर the search coil will enter the field. Point B के ऊपर it exits the field. So how would the shape of the graph look like? पहले मैं डायग्राम बना दूं, वो आप चेक कर लें, और ग्राफ के बाद नीचे एक्सप्लेनेशन है, उसको अप्लाई कर लेते हैं. मैं ग्राफ को थोड़ा सा डार्क एंड रेड कलर से शो कर देता हूँ. Your graph should basically comprise of multiple sections, which I'm constructing right now. Let's have a look. पहले मैं ड्रॉ कर दूं. So I'm trying to construct a sharp spike once at the point of entry. So the voltmeter will give you a sudden deflection, a quick deflection, and then goes back to zero, a sharp spike right at the point of entry. And then similarly, it stays at zero for some time. And then similarly, an identical spike, but in the opposite direction as it leaves the magnetic field. So yes, so from zero, the voltmeter deflects momentarily in one direction, something like a heartbeat, huh? And then returns to zero, stays at zero for a while, and then right at the point of exit, once again, there is a sharp spike, this time in the opposite direction, and then again the reading goes back to zero. So keep in mind, it's the change in cutting effect or the change in magnetic flux which induces EMF. तो रीजनिंग क्या देंगे ना, उसको देख लेते हैं. आई थिंक मैंने एक्सप्लेनेशन को 3 अलग अलग सेगमेंट्स में ब्रेक डाउन कर दिया है. अगर आप रीड कर लो, मैं थोड़ा सा कोशिश करता हूँ कि इसको जूम आउट कर दूं. सो इफ यू वांट टू हैव अ लुक एट द डायग्राम एज वेल व्हाइल यू आर रीडिंग इट, आई गेस मैनेजेबल हो जाएगा. तो स्टेटमेंट्स देख लेते हैं. तो as the coil enters the magnetic field, there is a change in magnetic flux. Therefore, EMF is induced. ठीक है ना? So right at the point when the coil enters the magnetic field for the first time, there is going to be a change in cutting effect. Consequently, an EMF is induced. Second statement. As the coil moves through the field, there is no further change in magnetic flux. So as the coil moves through the uniform field, there is no further change in magnetic flux. Therefore, the induced EMF stays at zero. And then finally, third wala statement, as the coil exits the magnetic field, once again, there is a change in magnetic flux, but this time in the opposite direction. Therefore, the induced EMF is now negative. Okay, so once at the point of entry, there is a change in magnetic flux, and once at the point of exit, Riha is asking why in the opposite direction. So Riha, think of it this way. Um, so at the point of entry, would you agree initial value should be taken as zero? At the point of entry, initial value should be taken as zero. And right as it enters, I'm assuming the final value to be NBA. So Riha, at the point of entry, the magnetic flux changes from zero to NBA. From zero to NBA. Okay, just keep that in mind. अब exit वाले point पे देखते हैं क्या होगा. So at the point of exit, the magnetic flux will change from NBA to zero, if that makes sense. At the point of entry, it was from zero to NBA. And at the point of exit, It will be from NBA to zero. So, अगर आप numerical terms में देखो ना, so if I call the first value to be above the axis, then diagrammatically the exiting point should be represented as a point below the axis. Hence, I went with an identical spike, but this time in the opposite direction. अच्छा यार ये अल्फाबेट्स में एरेज करता रहा हूँ जो रेलेवेंट नहीं है ना क्योंकि मैंने नीचे ऑपोजिट डायरेक्शन लिख दिया था सो आई गेस दैट काइंड ऑफ टेक्स केयर ऑफ दिस ऑलराइट मूविंग ऑन फर्दर मुझे एक सेकंड देना अब यार इसके बाद जो अगली चीज डिस्कस करनी है ना which naturally comes right after Faraday's law that is the application of Lenz's law so ये भी तुम लोगों ने ओ लेवल्स में किया हुआ था तो मैं थोड़ा सा आपको रिकैप पे लेकर आता जाऊं और फिर इसकी एप्लीकेशन देख लेते हैं let me break down the working into two separate diagrams. So this is your diagram one, and then I'll move on to the second diagram. Explain करने का काम यहाँ पे कर देता हूँ, and then I'll shift the slide onto a new one. वहाँ पे मैंने इसकी सारी wordings लिखी हुई हैं. So first of all, what Lenz's law used to state. So it's important for you to recognize कि Faraday's law क्या करता है और Lenz's law क्या कहता है. बिल्कुल simple terms में. Faraday's law कहता है कि a change in magnetic flux is going to produce voltage in the circuit. You may call it voltage, you may call it EMF, whatever desires you. Say, So Faraday's law just speaks about the idea that a change in cutting effect induces voltage in the circuit. Lenz kind of takes this idea one step further. So Lenz came up with this idea if voltage is going to be produced or if EMF is going to be produced, then certainly the induced voltage will give rise to the flow of induced current as well. Because wherever there is voltage getting produced, you would expect current to flow in the circuit. So Lenz's law tells us about the direction in which this induced current will flow. Okay, the Faraday's law deals with the idea that a change in cutting effect is going to produce voltage in the circuit. That's it. Lenz takes this idea one step further, and he states that the voltage must surely give rise to the flow of induced current. So Lenz's law is used to determine the direction of induced current. Right? So Lenz's law पहले understand करो purpose क्या है. So before you start reading the statement, मेरे पास जगह नहीं है वरना मैं कहीं लिख देता. So एक सेकेंड ना I'll mention it somewhere, don't worry. Not on this page, अगले वाले पेज पे. I'll just find some suitable place. मैं ये statement लिख दूंगा कि the purpose of Lenz's law is to help us determine the direction of induced current. तो अब क्या कहता है ना law और इसको demonstrate कैसे करेंगे. So he stated in his law that the induced current is always going to flow in a manner so as to oppose the motion of the magnet. So let me repeat the statement. So Lenz's law states that the current which is induced in the circuit because of the induced EMF, so the current which is induced in the circuit will always flow in a manner so as to oppose the movement of the magnet. Simple terms may induced current flows in a manner which will try to oppose the magnet's movement. So let's see how can we demonstrate this. Let's break down the working into two separate diagrams. So in the first diagram, let's start by assuming that we are trying to push the North Pole inside the solenoid. So arrow pointing downwards indicating that the magnet is trying to go inside the solenoid. If I ask you what pole is going to be induced at the end जहां मैंने क्वेश्चन मार्क लगाया है. Out of the two options, north versus south, based on what the law suggests, the pole induced must be such that it must oppose the motion of the magnet. So surely, north makes more sense. So as the magnet is pushed in, the solenoid introduces a north pole with the intention of opposing the motion of the magnet. ठीक है ना? अच्छा, रोहिल ने पहला ऑप्शन दिया था साउथ, तो आई थिंक अगर मैं साउथ लिखता ना, तो नॉर्थ और साउथ की ऑपोजिशन के बजाय रोहिल काइंड ऑफ अट्रैक्शन हो जाती. So based on Lenz's law, the pole induced must be such that it will oppose the motion of the magnet. It will stop the magnet from doing what it is trying to do. It will stop the magnet from doing what it is trying to do. So as the north is plunged in, surely a north will be induced. अगर मैं ये erase करके north को show कर दूं, and then if I ask you to use your right hand grip rule, so in case if you have forgotten के right hand grip rule कैसे apply करते थे, मैं आपको क्विकली एड्रेस कर दूंगा अगर आप भूल गए हैं तो. तो मैंने प्रीवियसली भी एक क्लास के अंदर शो किया था, तो दोबारा देख लीजिएगा. So in case if you have forgotten now, so right hand grip rule, wordings read कर लो, so then I can go back to the page. मैं स्टेटमेंट साथ साथ रीड कर रहा हूँ, होपफुली याद आ जाएगा. तो ये ओ लेवल्स में करते थे आप लोग. So if you imagine gripping the solenoid with your right hand so that your fingers follow the direction of the current, then your thumb will point towards the north end of the solenoid. ठीक है, so I'm hoping कि अगर wordings आपने follow कर ली है ना, so based on this wording, let me change the slide ताकि apply कर सके. ठीक है. So I'm back on my original diagram. So if you point your thumb towards the north pole, then your fingers would curl to indicate the direction of the current. So let me mark that direction of current with orange color or something. मैं मार्क करता हूँ, आप लोग जरा देख लीजिएगा if that suits you. So जरा थोड़े से लोग ओके कर दोगे कि you guys are so far so good with me कि यार वो एरो मैंने मार्क कर दिया है based on the right hand grip rule. So then I can extend the arrows and I can continue with the explanation of Lenz's law. ठीक है ना? Perfect. So let me just extend these arrows. And look carefully the direction of the induced current and the motion of the magnet. अगर आप carefully दोनों arrows को देखो, I'm sure Lenz's law की confirmation हो रही है. Look which way the magnet is moving. Downward. And look which way is the direction of the induced current flowing. Upwards से ज्यादा बेहतर y to x कहना होगा अल्फाबेट्स की टर्म्स में अगर आप कहते हो ना तो. बट अगर आप upwards ही बोलते हो तो भी it kind of makes enough sense for you to understand that what Lenz stated in his law kind of makes sense. है ना, that the magnet is moving downwards. ये सारे arrows वैरोज सब मिटा दूंगा मैं. ये बहुत अजीब लग रहा है. I'll show a demonstration in a proper form in the next page. ये तो सिर्फ explain कर रहा हूँ. ये सारे highlighted lines वगैरह यार मैं फिर मिटा दूंगा. So as the magnet is going downwards, The induced current flows in a manner so as to oppose the change causing it. है ना? So the fact that the induced current is flowing upwards, or you can say y to x, ना, so ये Lenz's law की demonstration हो रही है. तो ये downwards बता दूं, upwards बता दूं. I'll leave the arrows if you want. Uh, ये 50% of the job kind of gets done in diagram 1. Because then I'm sure इसका diagram 2 भी आना चाहिए ना, just for a full confirmation. In the first diagram, the North Pole was getting pushed in. In the first diagram 1, the North Pole was getting pushed in. So अब इसका बाकी का diagram का layout. So this time around, the North is going to be pulled out. Let me just zoom out a bit ताकि दोनों diagrams आपको नजर आ जाएं, just in case if you want. So this time around, the North Pole of the magnet is getting pulled out. So once again, if I were to ask you, which pole would you expect to be induced at the point where I have made a question mark? So again, between the options north versus south, keep in mind, pole induced must be such that it will try to oppose the movement of the magnet. It will not let the magnet do what it is trying to achieve. So the magnet, north pole, is trying to pull itself out of the solenoid. So not letting the magnet do what it desires means, I'm sure आप agree करेंगे कि अब साउथ इंड्यूस होना चाहिए. बिल्कुल सही है. मैं ड्रॉ करता हूँ. सो मैंने साउथ भी मार्क कर दिया है. इन केस इफ यू वांट ना, तो मैंने नीचे नॉर्थ भी मार्क कर दिया है. नॉर्थ मार्क करना शायद थोड़ा ज्यादा सेंसिबल इसलिए भी है बिकॉज अभी आपको राइट हैंड को प्लेस करना है ना. सो नॉर्थ को बना देना जरा बेहतर था. तो अब आप अपने थंब को नॉर्थ की तरफ पॉइंट करके चेक करो. सो पॉइंट योर थंब टुवर्ड्स द बॉटम ऑफ द स्क्रीन. Point your thumb towards the bottom of your screen and then see the direction in which your fingers are curling. And if you allow me to mark that direction on this diagram, I'll do that. तो तुम लोग जरा चेक कर लो. So let me repeat myself. Point your thumb towards the bottom of the screen where the north is induced. Check the direction in which your fingers are curling. And I've marked the direction of the induced current. So if I were to extend it, तो अगर आप टॉप वाले डायग्राम के साथ इसको कंपेयर करोगे ना, तो आई थिंक फर्दर वेरिफिकेशन भी हो जाएगी. And I don't think I need to explain anything else. आपको खुद ही वेरिफिकेशन नजर आ रही होगी कि this time the magnet has a tendency of moving upwards or outwards, and the induced current flows from induced current flows from, this time I should be saying x to y, or you can just say downwards. Once again confirming Lenz's law. ठीक है. So लॉ के स्टेटमेंट याद रखिएगा. लॉ का पर्पस याद रखिएगा which I failed to write. मैं कहीं अब जगह मुझे नजर आ रही है, so मैं पर्पस बढ़ा सा कहीं साइड पे करके लिख लेता हूँ. बट डेमोन्स्ट्रेशन इसकी कैसे करनी है ना, वो फिर मैं नेक्स्ट वाले पेज पे शो कर दूंगा. सो गाइज ये एरोज वेरोज मिटा रहा हूँ, अप एंड डाउन इरेज कर रहा हूँ, और आई थिंक आई हैव इनफ स्पेस. जस्ट मेंशन द पर्पस ऑफ लेंज़'s लॉ. आई जस्ट राइट इट डाउन दिस वे. ठीक है. सो एक सेकेंड ना गाइस, आपकी स्क्रीन पे जरा आ जाए, मैं वन को मैं पूरा रीड कर लूँ। आई थिंक इट्स देयर। मैं एरोज वगैरह भी बना दूंगा इस डायग्राम पे। थोड़ा सा छोटा नजर आ रहा होगा, बट आई वांट इट टू बी प्रेजेंटेड दिस वे ताकि दोनों डायग्राम्स नजर आ जाए। ठीक है, सो वर्डिंग मेरे साथ साथ रीड कर लेते हैं। मैं रीड कर लेता हूँ, इनकेस आपकी स्क्रीन पर अगर छोटा हो ना, तो यू डोंट नीड टू जूम इट इन, मैं रीड कर लेता हूँ। So the first statement tells you the purpose of Lenz's law. So Lenz's law is used to determine the direction of induced current in a solenoid. ठीक है, so kind of फजूल हो गया मेरा वाला लिखना, I should have checked it. According to Lenz's law, the induced current always flows in a manner so as to oppose the change causing it. This can be verified using the arrangement shown below. As shown in figure 1, when the north pole of the magnet is pushed in, तो मैं ड्रॉ भी करता जा रहा हूँ, पहले पहले रीड कर लूँ. So when the north pole of the magnet is pushed in, the solenoid, comma, current flows in the direction x to y. अभी mark कर दूंगा. That is, induced current opposes the motion of the magnet. Okay, next wala statement. As shown in figure 2, when the north pole is pulled out, comma, the direction of the induced current reverses. That is, it now flows from y to x, which again confirms Lenz's law. So, north pushed in, north was induced. The direction of the current, I'm marking it right now. And based on the wording, current flows in the direction x to y. Second diagram mein, when the magnet is getting pulled out, south was induced, north नीचे आ गया था, और ये सिनेरियो बन गया था. So this time current goes in the direction y to x. So if they ask you for a demonstration ना, तो ये figure 1 और figure 2 को यूज करके मैंने wordings पूरी की पूरी लिख दी है. 5 minutes रुक जाता हूँ before I continue. But before I give you a break of 5 minutes, remember the following statements because ये भी आगे चाहिए होंगे अभी. Induced current will not let the magnet do what it intends to be doing. ठीक है, induced current doesn't let the magnet achieve its purpose by opposing its movement. Guys, सब आगे की wordings हैं. So keeping in mind, every time when the magnet was trying to do whatever it was trying to do, the poles induced were trying to oppose the movement of the magnet. And keep that in mind because the next wording is based on that idea. Okay, when the magnet was being pushed in, the poles induced were not letting it go in. And when the magnet was getting pulled out, the poles induced were again opposing the movement of the magnet. So, on the basis of that, the statement suggests, मैं read कर लेता हूँ, जरा देख लेना. If a graph of displacement x against time t is plotted for the motion of the magnet, it can be realized that after a few oscillations, the amplitude will decrease continuously until the magnet stops completely. That is, we can say that the oscillations are subjected to light damping. Now, what's the reason behind this statement? So, reason for damping. So, as the magnet enters the coil, which was actually figure 1, its mechanical energy is used up in overcoming the repulsive forces between like poles. So remember when north was pushed in, a north was induced. Hence the wording. Its mechanical energy is used up in overcoming the repulsive forces between like poles. And as it moves out, slash away from the solenoid, which was figure 2, its mechanical energy is once again wasted, but this time in overcoming the attractive forces between the unlike poles. So are you guys okay with me कि मैंने क्या wordings लिखी हुई है? The reason why the oscillations are said to be subjected to light damping, or the reason why the oscillation will stop after some time, is because when the magnet was getting plunged in, when the north pole of the magnet was getting plunged in, there was a north pole induced, and mechanical energy was getting used up in overcoming the repulsive forces between the like poles. And similarly, as the magnet was getting pulled out, so the wording says, once again the mechanical energy is wasted, but this time in overcoming the attractive forces between the unlike poles. Hence, the graphical representation is the one that's shown below. So मैंने नीचे displacement against time का graph बनाया हुआ है. So the vertical axis represents displacement. The horizontal axis represents time. Now मैंने दो graphs construct किए हुए हैं. If you look at the graph which is constructed with the red color, and let me highlight that for you. So if you look at the red colored graph where the amplitude appears to remain constant, so based on SHM, simple harmonic motion, the red colored graph can simply be referred to as an example of free oscillations or an example of undamped oscillations. Remember, free oscillations or undamped oscillations were those in which the amplitude remains constant throughout. अब अगर आप इसी के साथ साथ ग्रीन वाले ग्राफ को ऑब्जर्व करो, अब एक्चुअली वो ग्रीन के बजाय ब्लू हो गया है बिकॉज मैं हाईलाइट कर रहा हूँ ना, सो आई चेंज द कलर. सो ब्लू वाले के अंदर यू कैन क्लियरली सी द आइडिया बिहाइंड डैम्पिंग टेकिंग प्लेस. मैं की के अंदर चेंज करके उसको ब्लू कर देता हूँ और नेमिंग भी चेंज करके उसको ब्लू से लिख देता हूँ, डैम्प्ड ऑसिलेशंस. ब्लैक से क्यों लिख रहा हूँ? ठीक है. सो इन दिस सिनेरियो, द मूवमेंट ऑफ द मैग्नेट, सिंस इट सफर्स डैम्पिंग, तो अगर आपको ग्राफिकल डिस्प्ले करना हो तो ड्यू टू लाइट डैम्पिंग बीइंग इंट्रोड्यूस्ड, सो द मोशन ऑफ द मैग्नेट आपके ब्लू वाले शेप को रिजेंबल करेगा. So the amplitude will progressively keep on decreasing until the magnet will stop moving at all. सही. So just remember the top statements जो मैंने underline किए हुए हैं. When the magnet was getting pushed in, its mechanical energy was getting consumed in overcoming the repulsive forces between like poles. And similarly, when the magnet was getting pulled out, once again its mechanical energy was getting consumed, this time in overcoming the attractive forces between unlike poles. So consequently, this continuous opposition is going to dissipate energy. So mechanical energy is wasted. Thereby, the amplitude of oscillation continues to decrease. So after a few oscillations, you would expect the magnet to completely come to a state of rest. See? Okay. अब एक final statement और बताना है before I conclude with today's class. ये underline statements हटा देता हूँ. Just give me a second. Now the question does arise, how can we reduce this damping effect? So ये जरा follow करना कि how can the damping effect be reduced? If I can manage ना, मैं इसको landscape में ले जाता हूँ. जरा सी wordings थोड़ी सी बड़ी हो जाएंगी display के हिसाब से. So let's have a look. So how can we reduce this damping effect? So the suggestion is, let's place a resistor in the solenoid circuit. And if you look at the diagram, you can see that I have placed a resistor in the solenoid circuit. Now, how will this reduce the damping effect? placement of the resistor, how would that reduce the impact of damping? इसकी wordings देख लो, फिर मैं conclude कर देता हूँ. The first statement, due to resistor, the induced current which flows in the solenoid circuit will decrease. है ना, resistor के आने से current का magnitude कम हो जाएगा. So induced current decreases in magnitude. Second statement, according to Lenz's law, the purpose of the induced current was that it opposes the movement of the magnet. Therefore, if induced current decreases, then the degree of opposition also decreases. रोहिल ने सही वर्डिंग लिखी है. अब तीसरा स्टेटमेंट, less opposition means that less energy is wasted. So less opposition means that less energy of the oscillating magnet is wasted. Therefore, more energy is left available for the oscillations to continue. Hence, we can expect the oscillations to now last for a longer duration of time. है ना, जरा स्टेटमेंट्स को दोबारा देखो कि the placement of the resistor will curb down this damping effect. It will reduce this damping effect. And how would it achieve this? The first statement, due to resistor, the induced current which flows in the solenoid circuit will decrease in magnitude. Okay, so the larger the resistance, the lesser is going to be the amount of induced current that will flow. According to Lenz's law, the purpose of the induced current is to oppose the movement of the magnet. So if induced current decreases, then the degree of opposition posed by it is also going to decrease. Less opposition automatically implies that less energy of the magnet is wasted. Therefore, more energy is left available for the oscillations to continue. Hence, we can expect that the oscillations will now last, comparatively speaking, for a longer duration of time. Now, if I ask you, कि आप ग्राफिकली इस पूरे स्टेटमेंट को कैसे शो करोगे? देखिए, मैंने नीचे ग्राफ बना के दिया है, उसको चेक कर लेते हैं, फिर कंक्लूड करता हूँ. Okay, so have a look. Red वाला graph is without resistor. Red graph without resistor. So let me mention more damping. Therefore, amplitude reduces at a faster rate. And with resistor, less damping. Therefore, amplitude reduces at a slower rate. मेरे पास कमेंट मैसेजेस में 3 स्टेटमेंट्स आए ना, मैं उनको रीड कर लूँ. रोहिल ने लिखा है द स्ट्रेंथ ऑफ द ऑपोजिशन. बिल्कुल सही लिखा है, बिल्कुल सही लिखा है, बिल्कुल ठीक है. रोहिल वाली वर्डिंग्स फॉलो कर लेना, वो वही वाला स्टेटमेंट्स हैं जो यहाँ पे लिखे हुए हैं. सो गाइज, इस पॉइंट पे मेरा ख्याल है मैं आज वाली क्लास को कंक्लूड करता हूँ. ऑल राइट गाइज, थैंक यू, टेक केयर एंड खुदा हाफिज फॉर टुडे.